essentially by receiving inputs. Let's try to illustrate this. Let's say this is a set of inputs, and then we have another box to represent the what usually known as the process, and let's call this one algorithm. And then we have another one that we want to denote the output. So we call this output. This is the process, and that's the input, and let's call this one the output. Now it receives a set of input here, processes it through some useful algorithm, and then generates some output. Whatever you have an input here, and the same algorithm, you are going to obtain the same output. No matter the number of times that you run the program, you are going to obtain the same set of output. If you change the input here and run it a number of times, you're still going to obtain the same output if you use the same algorithm. Now, to generate random number, we will use the pseudo-random generator concept, which is called the pseudo-random number, PSN. In such a case, we would have the ability to determine the relationship between the output and the set of inputs. We have several algorithms that run for random number generation. So to generate the pseudo-random number in computer, you won't be able to determine what output that will be produced in such a process. But however, if you run the program for a number of times, you might be able to identify some useful pattern to predict such a sequence. In the course of this random number generation, we are going to consider the linear congruential method and some other techniques. Essentially, we're going to look at the linear congruential method. Now, the linear congruential method is a very popular technique. It's widely used, and it is based on the modulus arithmetic. We can say that two numbers, x and y, are congruent. They are congruent modulo m if x minus y is an integral multiple of n. Thus, we can write x is equal to y modulus m. The linear congruential method generates random numbers by computing the next random number from the last random number obtained. Given an initial random number, let's say x naught, which is called the seed value, the method uses the formula xn plus 1 equals to bracket ax n plus c module m, where x naught represents the seed value. A and c must be less than the modulus m, where a and c and m are carefully choosing positive integer constants, of which a and c must be less than the modulo m. X naught is the seed or the last random number generated in the sequence. From the above formula, it shows that the random number generated must be between 0 and m minus 1. That is, the number must lie between 0 and the modulo. Since modulo produce remainder after division, hence the above formula will produce the remainder after dividing ax subscript n plus c by m. So to generate a random number between p and m, for instance, we have to use the formula x subscript n plus 1 is equal to ax subscript n plus c module m plus 1 minus p, or into brackets plus P for m greater than P. If the value of C is 0, the congruential method is known as the multiplicative congruential method. If the value of C is not 0, the method is called the mixed congruential method. The multiplicative congruential method is very handy. It is obtained using the general formula r subscript n equals to r subscript n minus 1 into brackets module m. This equation here will generate the multiplicative random number using the congruential method, where the parameters am are the seed and the seeds ro are specified to give desirable statistics. The properties of the resultant sequence, statistical properties of the resultant sequence, excuse me. By virtue of modular arithmetic, each arrow subscript n must be one of the numbers 0, 1, 2, 3 to n minus 1. Clearly, you must be careful about the choice of A and arrow not. The value of A and arrow not should be chosen to yield the largest cycle, that is the period, that is to give the largest value for n at which Rn equals to R naught for the first time. Now let's look at an example here to capture all the things that we've been explaining so far. If we use the mixed congruential formula, s subscript n plus 1 equals to a x subscript n plus c modulo m, and suppose that m equal to 8 and a equal to 5 and c equal to 7, and x naught, which is the seed value, equal to 4, we can generate a random sequence of integer as this. Now we're given the seed value to be equal to 4. Now, firstly, we will compute for x1. When n is equal to 0, xn plus 1 will give you x1 equals to 5 multiply x naught plus 7 mod 8. X naught is equal to 4, so we have 5 multiply the 4 plus 7 mod 8. So 5 times 4 is going to give us 20 plus 7 give you 27. 27 mod 8 will be equal to 3. Now, when you are dealing with modulo, if the number does not divide it totally, that is, if the remainder is not 0, it means that you just know the number of times that the modulo can divide the value obtained here, and the remainder would be the result when you use the modulo function. Now here the x naught or x1 is equal to 3. Then we use this value 3 to compute for x2. So x2 will be equal to ax is 5 multiplied by the value we got here 3 plus 7. So 5 times 3 is 15 plus 7, that will give us 22. 22 divided by 8, it can only go 2 times, giving 16. So remaining 6. So 6 is the x2 here. So from here, we compute x3. So we have it as 5 multiplied by 6 plus 7. So 5 times 6 will give us 30 plus 7 will give us 37. 8 into this will give us 32. Can go 4 times to give us 32, remain 5. So 37 modulo 8 will give us 5 here as x3. So from here we take 5 again to compute for x4. We have 5 times 5, 25 plus is 32 We'll do 8, completely divide it 4 times to give us 0 as the remainder, so we have 0 here. Now we'll do this till we get to a point where we come back to the same seed value. Now you realize that x8 produced 4, and the first value we had here, which was the seed value, was 4. So if you continue the sequence from x9, x10, you're going to obtain the same set of random numbers continuously. That is, from x1 to x4 follows this 3, 6, 5, 0, 7, 2, 1, 4, just like that, 3, 6, 5, 0, 7, 2, 1, 4, continuously. Now that forms a period or a particular loop based on the selected value for A, C, C, and the modulo. Now you have to note that the value of x8 is 4, which is the value of the seed number. If you compute x9, x10, it is the same random numbers will be generated like we mentioned before. You still also need to note that if we divide the random integers by 8, we obtain random numbers in the range of 0 less than x subscript n plus 1 less than 1, which is similar to using the round function of basic. The method of this random number generation by linear congruential method works by computing each successive random number from the previous, starting with the seed value. The linear congruential method uses the following formula this, and we'll say that the linear congruential method defined above has full period if and only if the following conditions are satisfied. 1. M and C are relatively prime. That is to say that there must not be any number that can divide M and C except 1. 2. If Q is a prime number that divides M, then Q divides A minus 1. The third condition is if 4 divides M, then 4 must also divide A minus 1. Those three conditions are essential for selecting A, C, and M in order to obtain a full period. If these three conditions are not fully satisfied, you would have an incomplete period in an attempt to generate your random numbers. Therefore, the value for A, C, and M are not generated randomly. Rather, they are carefully chosen based on certain considerations. For a binary computer with a word length of arrow bits, the normal choice for M is M equal to 2 arrow minus 1. With this choice of M, A can assume any of the following 1, 5, 9, 13, and C can assume any of the following 1, 3, 5, and